All right. Hello. Good morning, everybody, or good afternoon, good evening, wherever you are. Welcome to the third Rust Graphics meetup. And so this meetup is pretty cool. It's an opportunity to hear some more formal talks from some people in the Rust Graphics community working on different projects, working on cool things. And so we have three different talks today. If you go to gamedev.rs, we have our blog post there. It talks a little bit about the topics of the different talks, and then also it will have the links for the YouTube videos afterwards. And so if you're watching this later, and I don't know, you'd watch this like intro part later, but you'd probably find the links anyways. So we have three different talks. We'll be going for about an hour and a half today, I think. And so throughout this entire time, do make sure to post any questions either in the YouTube chat or Twitch chat, or on Discord as well in the game development and Rust Discord. We have like a meetup channel there, and so we'll be taking a look at that as well. And so without further ado, we'll hop right into the first talk, Hello Blade by Kvark. And so we will be right back with that. Oh, sorry, Kvark, looks like you're muted right there. Okay. The technical difficulties.
Yes, hello.
All right, perfect, all good.
Yes, great start. Thank you, Forrest. I've got something special for you today. It's called Blade, and it's a proof of concept graphics library I've been working on. Why another graphics library, you may ask? There's so many already. There's Volcano, there's GFX, Luminance, Sierra, RAFX. WGPU is, I think, used by most projects today, and it's hugely successful. Why do you need another one? Is the game dev not done yet? Can we finally start making games and not graphics libraries and not engine? So yes, this is all right. We have a good landscape. Libraries are great. They reach the level of maturity, and I'm very happy with the WGPU ecosystem in the way it is present today. However, I think the picture is not complete until we explore the design space for graphics libraries completely. And I found one area where we don't have anything yet. And I tried to build a prototype library based on this idea. And I will tell more as we go. It's called Blade. It's just a graphics library. The main motivator for this is my pet project, Rust Ventures. It's a render and a re-implementation of the old game. I talked about it a few times. We should show you've seen the screenshots. It has a lot of rendering. It has a lot of compute. It's full of experiments on how do we have different ways of rendering the terrain. I have like 6 different ways of rendering, entirely different. There's a lot of pipelines lying around, a lot of line group layouts defined. And I found experimentation on Ventures to be less ideal. And I thought maybe we can do better than this. It must be fun to experiment. I don't want to be dragged down by boilerplate where I don't care about it. Today, it has like 15 pipelines with 7 layouts. And before, when I had the GPU physics implemented, it had maybe twice as many. It has a lot of stuff in it. And we also see a big picture on for the last maybe 20 years or something, that you could move more and more computation on the GPU side. This a while ago, there was the approaching zero driver overhead paper showing how in OpenGL you can submit draw calls on GPU and do everything on GPU. And today we have a lot of compute happening and machine learning. And of course, one big area is ray tracing. It's really hard to find an example where you wouldn't want to do most things on GPU. To me, the only extreme example that comes to mind is GTA 5. If you're doing something like that, maybe you don't want to do most things on GPU. Otherwise, for example, in Vengers, once I had more than a trivial number of cars rendering, I figured that I would just use batching and do instance rendering. And with this, the number of draw calls reduced significantly. So wherever I went, there was always a way to have a low number of draw calls and a low CPU overhead for them. It's all about GPU. So a very important question is, why didn't I just evolve WGPU in the way that I want? And a simple answer is constraints. The WGPU as the top level library is constrained by the fact that it's a part of the Firefox. It has to run on many backends, and it's somewhat difficult to. It's not as fun to hack on because there is still a few layers down the ground. It's also safe. While for my cases, I thought it would be good to have something if you know what you're doing. So for most cases today, for most user applications, WGPU is absolutely the right choice. But I thought there's still a few cases where I know for sure how to debug on native APIs. I know how to implement it. So I just need more ergonomics, and I need to be closer to the metal. So what about the WGPU HAL? I did try to evolve HAL in the direction that I was thinking. Like I made a PR that made HAL objects copyable, and that's copyable objects is something very silly, but it's super convenient. In terms of ergonomic, just being able to put your handle to a buffer somewhere without caring about the fact that it's a unique handle makes your life much easier. So it turned out that I can't really evolve WGPU HAL in this direction. Moreover, it supports more backends than I currently care about, and these backends carry the limitations on their own. In particular, D3, D12 is very constrained. So let's think about this question. Programming is all about managing complexity. Where does the complexity live in these libraries, in the full stack of those libraries? And I made this chart, which is a little bit silly. Don't take it literally. But the main idea is, in case of WGPU, all the complexity is managed by the library itself. So, well, most of the complexity, sorry. The part on the right, the red part, which is the user, is where the user defining the layouts for things. And WGPU has a way for layouts to be derived, but you still need to create the bind groups and manage them. And most things happen inside the library. The library tracks all the resources, validates and inserts the transitions. So this is where it lives. In WGPU HAL, it's completely zero. Library doesn't do anything. And that's the point of WGPU HAL, is that you as the user decide how to use the GPU. But it's not ergonomic at all. Writing for WGPU HAL manually is a little bit involved. It's not as involved as Vulkan, but it's still involved. In Volcano, it's kind of hard because I don't know very well. I think a lot of complexity is managed by the type system, but I don't know exactly how much. it's still a very low-level API. It's basically Vulkan. So I put user as the dominant factor. And finally, Blade. You see, Blade is very different according to this metric because it is trying to make the driver do all the work, not the user, not the library. The library is super thin. It's basically very, very pass-through. The user gets a very ergonomic API, and the complexity is managed by the driver. How do we do this? Let's start with the state tracking. That's one of the important bits. In other low-level APIs, you care about the access for resources, and you care about image layouts. And you transition images between layouts. You want to render to a render target, you transition it to the render target optimal, you render it, and you transition it back to the sample, and so forth. These transitions are encoded and validated by your Vulkan implementation, and you have to take them into account when writing code. And WGPU mostly handles that for you, mostly because you can still get in a situation where you're doing something invalid, and it will tell you. In Blade, there is no pure object state at all. And this is achievable because Vulkan has a general image layout, which can be used for everything. And the same for Metal and the same for OpenGL API. With the general layout, you don't actually need to transition the layout, but you still need to transition the access to the resource. And for this, Blade uses global transitions only. So there is no per object image layout. There is no per object access patterns. There is no per object anything. You just write passes like here. Where the pass ends, there is a global barrier. That's it. So as an outcome, you would think that this is maybe not the most efficient on GPU, but evidence suggests otherwise. In terms of the global barriers, I'm talking about cases where you do most things on GPUs anyway, so you don't have a huge number of passes, and and a few barriers between the passes do not contribute to anything. You will not see it on your profile significantly. In terms of the image layout, the fact that I'm not using the optimal layouts for any operation is only matters for a few GPUs. And today the industry seems to be leaning toward an approach where it doesn't matter at all. It's a big surprise, but again, I'm talking to you on the laptop with 6850U AMD APU. This is one of the latest models of AMD APUs, and running a benchmark of Blade basically becomes GPU limited, the same as WGPU, even though Blade doesn't care to set the render target optimal layout. So this means that modern GPUs and drivers, they either don't care or they have the hardware to actually compensate by the fact that you are not in the right image layout. So in the end, it doesn't matter that much. And maybe we don't need to pay that. So with Blade, I'm trying to explore this area where most of the work is done by the driver itself, and the driver will know what is important and what is not.
Sorry, Quark, just to interrupt quickly. The message you are streaming to the screen is visible, and it's just including some of the stuff.
Whoa, okay.
Perfect.
Yeah, thank you. Yeah, so ergonomics of this is very simple. You create a resource, you use it, you submit the command encoder. That's it. You don't care about transitions. The only one tiny single bit you care is initialize image thing, because you need to transition from an initialized layout to the general layout. So a one-time encoder operation for any texture that you create. That's all. Then we go to another big thing, the binding model. It's arguably one of the biggest differentiation factors between the low-level APIs, and that's what WebGPU group spent ages discussing on how to do it properly. WebGPU ended up with a Vulkan-like binding model, and that's probably the biggest differentiation factor between WebGPU and Metal today, that it uses the Vulkan binding model. In Vulkan binding model, you create a descriptor set layout, and then you create a pipeline layout. And then when creating a pipeline, you give it a pipeline layout, and then you just allocate descriptor sets as if you're allocating memory, and you bind those descriptor sets. And it's a lot of work. It's most work you're doing, most boilerplate you're doing in your code. And this binding model management in trusty vendors is taking a lot of code, which I don't think it's valuable. So in Blade, you don't have any of that. You don't have layouts, no bind group layouts, no descriptor set layouts, no pipeline layouts, and no sets either. It's magic. You don't need descriptor sets. It turns out you can just create your pipeline and bind your data. Everything else is handled by the driver. And on top of that, the cherry on top is that there is no uniform buffers. If you are drawing something, you need some data, you just pass this data in directly. That's it. You don't care how it gets to the GPU. You don't care about whether push constants are available and what is the size of them. How to manage your uniform buffers, how to circulate them, how to prepare them before the render pass, because you can't do transfers inside the render pass. All that boilerplate, all that headache goes away. You want to render something, you just say, I want to bind this struct, and it has some plain data in it. That's it. Like here, this is how you define those structs. Foo is effectively a bind group, but you don't need the layout. You just derive the shader data for it. It contains a texture and a uniform buffer. Where the uniform buffer should be, you just provide a byte mock, the plain old data structure. That's all. When creating a pipeline, you give it the layout derived from this shader data struct. The syntax here is a little bit unfortunate that you have to do foo as shader data, but I think it's bearable. Every pipeline in Blade has its own layout, and this goes across those Vulkan folks who specifically want to share the resource layout between pipelines. Well, guess what? D3.12 doesn't have that at all. In D3.12, you basically have a new layout for every pipeline at the API level, not even at the driver level, but at the API level. So it's a strong evidence that maybe sharing resources between pipelines is not really that important. And if you're not doing this, the binding model simplifies significantly. If every pipeline has its own pipeline layout, implementation becomes simpler. Like I can do OpenGL backend with way less code than WGPU HAL because I don't want to share data between pipelines. It's all contained. This is how you bind it for drawing. You just say, my bind group 0 gets this structure. That's all. And another funny thing you may see is that my texture view here is an actual texture view. It's a Blade texture view. It's passed by copy, not by reference, but by copy. And this is because all the object handles, like resource handles, are copyable and they're designed to be small. They're just a few machine words of data. So they're designed so that you're able to just pass them around as needed. You can create hash maps of them. You can just pass them in functions, anything. Writing for this model is really, really ergonomic. It's making things so much more enjoyable for me to write. So I'm looking forward to build more things in it. I have a few examples right now, which I will show. But the ergonomics part is achieved in this proof of concept. library. And I even would go as far as to suggest that maybe WebGPU should have done the same for the binding model, because it's not like you're going to build GTA 5 on WebGPU either. So there's other constraints in place, and making it simpler would definitely benefit it in the long run. Maybe there is still something to consider. Oh, those of you with the low-level background may wonder how this is all working. Like, why do I not need the uniform buffers or descriptor sets, or especially on Vulkan? So Vulkan has a few things to help. I'm still prototyping. I'm still not completely sure where I'm going to settle, but it has the tools to implement this. The thing that's used in the published crate right now, and it is published as of a few days ago, is using inline uniform block and associating every command encoder with a descriptor pool. So if you bind something, you have a descriptor pool. It just allocates the descriptor for you and binds it instantly. You don't see that. And the uniform data is inlined in the descriptor itself. So this is, for the driver, it makes it very convenient. And when you reset your command encoder, the descriptor pool is also reset. So the lifetime is very clear. There's no confusion for the driver or for you on what the lifetime is. And you can bind a lot of things this way. I was surprised to know how much stuff you can bind per frame without slowing down on CPU. The other thing that Vulkan can do is the push descriptor sets, but I had a few problems with this, but I'm still considering this on the table. All right, so this simplification allows there to be very, very little code. This comparison is completely unfair. Like, don't use it anywhere. Completely unfair because RAFX and WGPU are way more mature. They have a lot of things in them, good logic that is required. But in Blade is just a proof of concept. Right now, I see that it has twice as few the lines of code for Vulkan and Metal than other libraries, and OpenGLES is even less. So all of the backends are within something like 2,000 lines of code. That is absolutely nothing. It's super, super simple inside. Very easy to debug and reason about. Yeah, with all those shortcuts, with the resource states and bind groups on the fly, how can I do draw calls? I mean, I could say that maybe the applications you write in Blade just don't do a lot of draw calls, and that would be fine. As I said, it's not for GTA 5 kind of scenario, but so far from what I measured, it's actually very fast. I can do on an old MacBook Pro, I can do 20,000 draw calls with a unique descriptor set each per frame for 60 frames per second. I think that's enough, right? How many of your games do more than 20K draw calls? Right. So on this laptop that I'm talking to you right now, the benchmark goes into 50K draw calls, and it's still not CPU limited. It becomes GPU limited for both WebGPU, WGPU, and Blade. So basically, it's fast. Now, Blade is a lean and mean library. And we talked about the lean part. What about the mean part? It's totally unsafe. Yeah. Again, the idea is you know what you're doing. You know the APIs you're targeting. You can use the GPU tools, the validation layers. It does help you enable them, but you know how to read them. And this is basically what I do for myself. I do know how to read them, and I want to be in control. So it is unsafe. It's As I said, there's no tools involved. And it is incomplete too. It's a proof of concept so far. For example, I have only a few texture formats right now. I don't have any vertex buffers. Who needs them anyway? You can just bind the buffer and index it with your vertex ID. So there is one object responsible for the context, and it contains your queue and device and everything, and it's internally synchronized. This is also a big experiment in the workflow scenario. All the libraries I made before, there's sort of implicit expectation that I'm going to maintain them and fix them. Here, I'm honestly, I cannot provide that. I admit I cannot allocate time to maintain it like all the other libraries. And I directly recommend everybody to read what it feels like to be an open source maintainer article. It's enlightening, and I relate to this so much. It talks about the life of a maintainer and what a day looks like, basically, for a maintainer. So here, I want to try a different model. As you see, Blade tries to be very different from other libraries. So it's also about the workflow of development. I'm going to try the model where you take it and you customize it for your needs. Like you're making a game, let's say Avengers or Valorant or any other game, basically, and you need a graphics stack, you need some backends, right? So you just take Blade, you put things in it that you need. Maybe you come back to upstream and suggest and do pull requests, maybe not, up to you. So this is very mean. I'm sorry about this, but that's the only I can do in my situation right now. I mentioned before that objects are copyable. This is what the buffer looks like in Vulkan. It's basically 3 machine words. You can copy it around. Now the context, the global context, I call it global. It's still an object, but it's an internally synchronized object. Like you create resources, you submit your command buffers. It's all you take it immutably, so you can put it in an arc and share it if you need. It's very convenient, and also it does kind of abstract well, because on Vulkan the device is internally synchronized, the queue is not, and on Metal everything is not internally synchronized. So I know where to do lock-in and where I shouldn't do lock-in, and this is a part of the implementation. You don't care about this. You just consider everything internally synchronized. This is a thing we can't get around. We need shaders. So for Blade, I'm using the state-of-art shaders, which is Wixel shaders, which is a web GPU shading language. But it has a nice, it has a very nice property here. Because as you know, in Wixel, you generally annotate your resources with binding and groups. You know where in the pipeline layout your resource should be. So in Blade, there's no pipeline layout. You just declare resources. That's it. Like I need a sampler. I declare a sampler. This is one of my favorite parts. It's matched by name on the Rust side. So your fields of the struct that you're providing for the shader data match by name with the variables, the global variables in your Wixel modules. And this is how binding is done. So the nice part about it is that writing shaders, you don't care about the layout. Just declare what you use, and that's it. The hidden nice bit is that it's actually almost a valid Wixel module, almost in a sense that you can use Naga to validate it today. I added a flag to Naga that allows validation without the binding decorations. So you get complete tool support for your shaders. You get complete validation. You can make sure that they work. And yet, when you instantiate the shader for the pipeline, It will build the pipeline layout and actually inject the Naga module decorations in the modules that it loaded. So everything is handled for you. Oh no, this slide is too big. We don't see it, right? Yeah, so going closer to the conclusion, why would we use Blade? You use Blade because it has great ergonomics story. It's made for ergonomics. I would say if you are building an unsafe library and you can't basically limit the unsafeness, at least make it ergonomic. This is what Blade does. It has very simple synchronization model, very simple binding model. It has true Wixel shaders. It's lightweight. And let's see if it lets me. Oh, it doesn't even let me see the thing. Okay. Yeah. Just, okay. Okay, what happened? Did I lose it? Yeah, that's better. And all the objects are copyable. You can move them around, and it has a context that's convenient to use. These are the reasons to use it. Reasons not to use it is that it's very incomplete. It's not going to be actively maintained in a sense that I'm going to maintain it for my needs. And if you have something you want to add, I will consider that adding upstream. And if you are not entirely sure what you're doing, then you shouldn't be using Blade. All right, let's run some demos here. So this is the benchmarking example I used, where you spawn a bunch of bunnies. It becomes slow here very early because it's in debug and we are actually streaming. But in release without streaming, I reach 50K bunnies and become GPU limited. It tests, every bunny is drawn with its own bind group or descriptor set. So it tests the binding capabilities. It's not instanced in the way you would be doing this in a real game. Again, no validation errors. It's running on Vulkan in this case. This is a particle system. And as you can see, I have a eGUI integrated. So eGUI integration is like really, really simple because the binding model is so simple. You can tweak some parameters. This is doing a GPU simulation of particles in compute shaders. It is doing instancing, and there's like 20 or 200,000 particles. There's a lot of particles, basically. That's what you would do on GPU particle system. Also, there is a thing I should show you as well, which is important. Okay. Yeah. The backends I have are Vulkan, Metal, and OpenGL ES, mostly for the web. So here I'm running the run WASM on my machine so that it can create a local host. I can open it here. Okay, see? So we just built for the web and ran the same demo on OpenGL ES3, and it runs. There's very little code there. It seems to work so far. So here we are. The repo is now public. Again, it's a very different library from what I used to do. And it's a big proof of concept. And I'm excited about the ergonomics of it. And I want to try it in more contexts. that's all. Thank you for listening.
Awesome. That's super cool to see more progress in the graphics API space. Um, of course, as soon as I start talking, my dog starts barking. So, got a few questions here from the Discord. I put the Discord link in the YouTube chat. If anyone on the stream wants to join, I will also copy that over to Twitch chat in a second. So, from Noxum, if the core ideas are that the low-level APIs are not required for that, sorry, if the core ideas are that low-level APIs are not required for performance and user space state tracking has ergonomics overhead, what does Blade bring to the table over existing cross-platform APIs like WebGL?
I think, yeah, I think the question is formulated a little bit incorrectly. You, yeah, I'll try to answer the last part of the question. So what does it give you on top of the WebGL? That's the question. OpenGL is deprecated on all platforms today. I know this is controversial, but on Linux, all the vendors only want Vulkan. On Android, all the vendors want Vulkan. If you run an OpenGL application, they want you to basically run through a layer that translates it to Vulkan anyway. So on Linux, OpenGL is legacy. On D3D, OpenGL has always been legacy. On macOS, it's been legacy as of 3 years ago, and now I don't recommend you running anything. So I don't think it's a good choice, and Blade is going to be much faster than OpenGL because it still uses a better model for the interaction. You still have passes, the concept of passes. You still have the concept of pipelines. There is still bind groups involved under the hood. So I think you would get a better outcome with Blade. Yeah.
Cool. I think I'm getting some issues with posting the Discord link due to spam filter, so I'm looking at getting that solved. Yeah, let's see if there's anything else in here. I really like the idea of having the everything just be immediately bound. I'm kind of curious, how do you deal with those sort of large scale buffers that you do with like any kind of GPU powered anything where you have how would you say bind your vertex buffer without uploading it every time?
Right. Only the uniform data is inlined. You can bind the storage buffer like a buffer.
I see.
Yeah.
All right, that makes sense. Yeah. Unless anyone else has anything else, I think we are ready to go. And in a minute, we will get back to the next talk, implementing an extensible renderer.
Welcome to my talk on implementing an extensible renderer. It's been a while since I spoke about my rendering project called Rafix, mainly because I haven't been actively working on Rafix. 2022 was a very busy year for me, so I haven't had as much time to work on it. That said, this break from Rafix has been a good opportunity to think retrospectively about the last couple of years that I've worked on it. I want to focus on some ideas that I think are worth sharing, instead of talking too much about Rafix itself. I'll touch on some things in graphics to make concrete examples, but I think this talk is more interesting if it's useful to people whether or not they want to use graphics. First, some background on the project. I wanted to make a viable start towards a renderer that could be used in real shipping games. To me, that means productive workflows for implementing rendering techniques and getting content onto the screen. This was also a learning project for me. My experience in graphics before this project was a little bit of DirectX 9 in university on student projects quite some time ago. Modern rendering APIs today are quite different from what was available at the time. When I started the project, it was Vulkan only, and I was focusing on the basics, like rendering quads, some normal mapping, and eventually some very basic lighting. I worked with Carl Bergstrom, who had a project at the time that would eventually become Distill. It implemented file change detection and provided a way to process assets and stream them to a remote device. In this demo, all of the assets like textures and meshes are streamed to the mobile device. And when I change the scene in a text editor on the PC, it streams changes to the device. After hitting this milestone with a fairly dirty prototype, I spent a lot more time on foundational aspects of the renderer. I transitioned from working directly with Vulkan to having separate backends for Metal and Vulkan, and eventually GLES 2 and 3. I also added a render graph, some rendering techniques like shadows, and a better pipeline for handling shaders. I also spent some time learning how to use Blender and writing a custom exporter to get full scenes out of Blender and into the renderer more easily. In this demo, the scene is exported via the custom Blender plugin, making it much easier to iterate on. In late 2021, the overall architecture had taken shape. I implemented a second pipeline for higher fidelity rendering to take advantage of newer hardware, while still having some support for web and older hardware. I was able to implement a lot of new rendering techniques quickly, using the tools and workflows I had built over the previous year. I'm especially happy to have implemented GPU-driven rendering with occlusion culling, and implementing my own TAA was also a great learning experience. I'd like to briefly pause and give some encouragement to anyone who may be just getting into graphics programming. My experience with learning has been very rewarding, and looking back, I think the difficulty is not that any one topic is necessarily hard, just that there are a lot of topics. But this means they can be tackled one by one. Time and persistence can lead to real progress. Now I'd like to discuss some specific ideas in graphics that make it extensible. First, the crate structure is incremental, adding functionality and optional layers. Plugins allow new functionality to be implemented non-invasively. I'll focus on 2 of the 3 plugins that exist in graphics in this talk. Finally, I'll discuss the extract and render resources, which allow plugins to share data with each other and the application without unnecessary coupling. The core rendering logic in graphics is split into 4 layers, with plugins that add functionality. The layers can add functionality and helpful utilities, but become more opinionated. The responsibility of the layers are clearly defined and they aren't cyclically intertwined, so you can use what you need and ignore the rest. First, Graphics API implements an API abstraction layer. The internals are left exposed, so it's easy to work directly with the hardware API when it makes sense to do so. Next, the framework layer adds a lot of helpful utilities, such as a render graph, delayed resource destruction, descriptor state management, and a pipeline cache. It also includes the shader processor, a utility that reads GLSL code and generates compiled shaders, reflection data, and Rust source code that provides strongly typed APIs that greatly ease producing data to be consumed by the GPU. The asset layer adds distill as a dependency, allowing code to load an asset by path or ID and related GPU resources to be automatically created. The renderer layer sets up a swap chain and render thread and provides a skeleton that the plugins can hook into. Graphics comes with several plugins and a Blender extension for exporting whole scenes. Users can also add their own plugins. And finally, the application creates the window and enables the required plugins. The first kind of plugin I want to discuss is the feature plugin. A lot of what it does is based on this talk. While I'll mention a few of the concepts from it, please check out the original material. A render phase is a time to draw things, usually during a render pass. For example, the skybox, the shadow maps, opaque, transparent, or UI. A render feature is a thing to draw during one or more phases. For example, a mesh, a tile map, a skybox, or things like that. A view is like a camera, a frustum, and which phases should be drawn. For example, the mesh render feature may draw during shadow map, opaque, and transparent render phases. There might be a view per shadow map, which just enables the shadow map phase, and a single view for the scene that enables the skybox, opaques, transparents, and UI. The outcome of this is that the shadow casting meshes are rendered to the shadow maps with one shader, while for the main camera view, the meshes are drawn in the appropriate order with a different set of shaders. All features are drawn in 3 steps. First, we extract the data we need to draw the frame from game state. Next, we do any CPU side work required before emitting draw calls. For example, we might have a claw simulation. Finally, we emit the draw calls to command buffers. I've left out a lot of details, but to touch on a few key advantages. This architecture allows unrelated rendering features to coexist. It also allows a render pipeline to control when the features draw, all of this with as little coupling as possible. There are many other advantages. Please check out the full talk for more details. Next up are pipeline plugins. And here I mean pipeline in the sense of steps to draw the frame. For example, Unity has 2 pipelines, the lightweight and the high definition pipeline. The role of the plugin is to schedule CPU and GPU work needed to draw the scene. Only one is active at a time. Typically, the plugin will define and execute a render graph, but this isn't required. It could be arbitrary code. A lot of resources are available to read about render graphs. I think they make a lot of sense if extensibility is at all a priority. In Graphics, the render pipeline plugin generally produces a render graph per frame. The parts of the graph that are active will change depending on game state as well as graphics setting. AMD recently introduced render pipeline shaders, which I think are worth the look as well. They showed some very promising results. Making this concrete, Graphics provides 2 pipelines, which are really generating 2 render graphs, with a lot of the same render phases and features. The basic pipeline is highly compatible, while the modern pipeline is more forward-looking. That said, they still share a lot of code. The takeaway here is that a lot of basic functionality can be shared even while supporting multiple pipelines. Finally, I want to talk about extract and render resources. The purpose of this system is to support passing data between the application and plugins, as well as between plugins. This will be familiar to anyone who has used an ECS. Arbitrary structs can be inserted and looked up by type. Sharing data in this way reduces coupling, as it avoids the assumption that a specific plugin is being used. It only requires coupling to the struct, which is acting like a contract for the kind of data to be shared. Implementing this doesn't require much code, and it's easy to find example implementations of it. Graphics has 2 flavors of resource maps. The extract resource map is rebuilt every frame and just has references to game state. Render resources are persisted across multiple frames and mainly used to share data within the render thread, or to pull data from the render thread back to the game thread. So for some example use cases, an application can publish data to plugins, such as setting a graphics option like enabling or disabling bloom. A plugin can publish data to other plugins, such as a pipeline plugin, pushing shadow maps to the mesh feature plugin. Plugins can also publish data back to the application, such as debug data. To summarize, render features allow sharing and reuse of basic stuff that many of us need. Definitely check out that GDC talk. Render graphs and pipeline plugins can control rendering features without direct coupling directly to them. And a resource map allows for sharing data without too much coupling. I also think this allows for batteries included approach to make a render more approachable and productive, while also being flexible enough for power users. As for what's next, I think renders are more fun when they have content to draw. And managing that content, particularly in a way that lets people work in teams, is very hard. I think a solution, in the form of a content pipeline with tooling, could be Rust's killer app for game development, and a potentially good inroad for Rust to be used in commercial games. But this is hopefully another talk for another time. Best wishes in the coming year, and thanks for listening.
Sorry, I was muted. Let me do that again. Okay, so that talk was pre-recorded, and so if you want to ask questions, Klizma is in the chat, or if you go to the Game Development and Rust Discord, Klizma is there as well, so you can ask some questions about the progress on Rafix and how things are doing. And so let me just check chat. Yes, it's telling me that I'm muted. Very good. That happens quite often. And so, anyways, we're pretty on schedule. We have one more talk before the end of today. And so we will be right back in just a minute with Ren 3, high performance cross platform GPU driven rendering in WGPU and Web GPU. All right, Connor, I'll hand it over to you.
Alrighty. Let me figure out how to go full screen.
On Firefox, I feel like it's either F11 or like Command Shift F kind of thing.
But why is this all weird? That's
Yeah.
a slide mode. There we go. Ha!
Perfect.
Victory. Alrighty. So we are looking again at Ren 3. This is my looking at how we're now doing GPU-driven rendering in a way that is compatible with both native WGPU and baseline web GPU, and some of the fun things you can still do with all the new powers that you get in web GPU. So, just a little background. Who am I? I am a professional graphics engineer. I co-maintain WGPU, and I am the benevolent dictator for life of Rend 3, a WGPU-based 3D rendering library that we're going to be talking about today. So, I did a lot of talks. I did a talk at the first graphics meetup about the CPU side performance of Rend 3. And I promised that one of the following talks would be about GPU side performance, and this is that one. So on a kind of intense scene, you can see that this is what our GPU profile looks like. It is mainly doing a whole lot of nothing. This isn't great. We can do this a lot better. For context, if you haven't seen one of these graphs before, this is basically a graph of occupancy. So the green is the vertex shaders, the blue is the pixel shaders, and it shows if you're all the way at the top, you're using the maximum potential GPU programs running at once. And if you're very low, it means you're not actually using the compute cores as much as you can. So I skipped a whole set of slides. Woohoo. So some of the goals of Rend 3, which we'll get, that slide was alluding to, is performance. We want performance without sacrificing usability. We want the first use and the initial use of the library to be easy enough that you are not you're not inundated by writing 1,000 lines of code to draw a triangle, or that kind of thing that people often get stuck on. At the same time, not sacrificing usability. We actually do a lot of things very similar to how Graphics does through layering, though our layers are a little different. I actually talked a little bit about this in the first talk, but it's evolved since then, and probably should revisit it in a future conversation. We want first-class support for user-generated content. This is actually really the inciting incident that caused me to want to make Rend 3, is that I was making a game, and I wanted to use Unity, but all of the content, all of it, was actually provided by the users, because the game was essentially just a container to run mods. So when I was looking into Unity or Unreal, their support for user-generated content is there, but it means you're sacrificing the majority of the light baking, all these other features that you really need to get Unity to perform well and look good. So I wanted to build a solution that would get that that middle ground going. And finally, despite the usability on the first level, we have to be able to modify what the renderer does. I am very much of the opinion that there is no such thing as a game that has properly shipped without somehow modifying the renderer. It's basically just impossible. So we need to be able to facilitate that if we want people to actually be able to ship on this product. Are you going to go down? You are. So this talk is going to be focused on GPU performance. We've been there. Over that slide too early. All right. So user-generated content poses a lot of interesting problems. We've already talked about how it's provided at runtime on demand. So this prevents a lot of the pre-baking and the sort of asset pipeline side of what a lot of games would use. They're a component of highly dynamic. They're often a component of highly dynamic worlds. Things that have user provided content often are constantly changing, have people contributing, removing, modifying the world. And that is another issue that causes a lot of tension against the asset pipeline kind of model where everything is pre-baked. If it's coming from users, it's often coming from non-standard asset pipelines. It's coming from, people just modeling stuff in Blender. It's coming from, people, sculpting stuff. It's coming from wherever and then just exporting it. It's coming from people, unfortunately, extracting from other games, taking the models and throwing it into your thing. So there's no real standardized asset pipeline. And the people who are making it, you have no control over. So you can't tell them to use a standardized pipeline. They're just users of your product. And if you were to tell them to do something, some of them would do it, but another chunk, may not be reading your communications, may not care that much. So this is very much a situation where the onus is put on the program to deal with the consequences of the sort of generic assets that are provided. Sorry, let me just, that's, okay. So often, some issues with this user-generated content in practice is that it often has a very high poly count. Particularly, it has a disproportionate poly count. Normally, when you're dealing with scenes, you allocate polygons to where they're needed. So, a gargoyle up on a building will have 1,000, and a statue right in front of your face of the same size might have 10, 20 times the amount of polygons, because you will be staring at it directly as opposed to off in the distance up in the sky. This is often not the case. People model what they model. They may not know how to retopologize, so that's kind of just what you get. There's also a constant lack of LODs, because generally most model formats that you ship stuff with, at least today, don't really support LODs. GLTF doesn't. There are extensions for that, but good luck. And may have poor topology that would make automatic decimators have issues. Tools can help here. There are things that you can provide as a user as a developer, to be like, oh, when you upload your thing, I'm going to audit it and say oh, it has 15 million times more polys than it should. They might listen to that, they might not, because they're totally allowed to just not listen. So this is the problem I really want to be able to solve. And a lot of these performance techniques need artist help. And some others need processing the asset pipeline, and then this just puts us in a pickle. Aklisma also mentioned on Discord that even if you have a dedicated asset pipeline, not requiring pre-baking opens up a lot of possibilities for making things quicker, etc., which is a very good point. So going on from there, so we want to optimize our GPU time. Our CPU time has already been optimized to hell and back from the last talk, or from the first talk. So if we look at the actual performance traces, they look GPU bound. Sorry, one second. There we go. They look geometry bound, and some additional constraints here. Metal, I talked about this at the previous talk. We used multi-draw indirect to do all of our GPU-based culling, to draw the results of all the culling. This is kind of a problem because Metal doesn't have it. It does, but it doesn't. Not in a way that is accessible to WGPU, at least. And DX12's multi-draw indirect is also limited due to a very similar reason. Basically, they need special buffer formats, and we haven't implemented all that transforms yet. Additionally, WebGPU just doesn't have bindless. This is fine for the hardware they are targeting, but does add another limitation. And ideally, we want one system that will work on both a bindful and a bindless system. Meshlets often are thrown around a lot, and we'll get into that a little bit later. And my basic thesis is that if we cull geometry aggressively, we will go faster. That's based on that trace that I showed before. That's sort of where I'm thinking with all of this. So, let me be on the right window. Meshlets. So meshlets are kind of a buzzword at this point, and essentially you take a mesh, you split it up into a bunch of tiny meshes. Each individual meshlet is completely standalone. It has its own little vertex buffer, its own little index buffer, and you can do a bunch of fun things with this, including using the new mesh shaders, which sort of accelerate this kind of pipeline. However, they're actually quite limiting in a lot of ways. They require processing of meshes into meshlets because it's not trivial to go from one to the other. Often you'd use something like meshopt, but that's a CPU side slower process. How would that deal with GPU generated meshes? Say you have an ocean simulation, say you have whatever running on the GPU generating geometry just in time right there. How do you do that conversion? I'm sure it is possible, but that's a lot of extra work and a lot of extra complexity to deal with uh, when you're trying to uh, when basically we're already racing against the clock to make these things run quicker. So we've decided against using meshlets, but meshlets are not. Some of the takeaways from meshlets are still usable even if you're not using meshlets directly. So my whole strategy is based around triangle culling, and this was most helpfully described by Graham Willadahl at GDC 2016 as part of a presentation by Frostbite. I highly recommend reading it. This is going to basically go over the basics and a lot of the like more nitty-gritty implementation stuff, but the theory and the math and what it's actually doing in the shader is all in that talk. Highly recommend reading it. I've had that thing bookmarked for multiple years at this point. So, but to sort of summarize, in a compute shader, for every single triangle on the screen, check if it has a zero area, so that if it's degenerate and it has no narrow area. If it has a negative area, it's a backface. You can do this all in one check, by the way. The talk has, or the slideshow has more information on that. Micro triangle. So this is a triangle that is so small it doesn't actually intersect one of the points that the rasterizer is sampling. So it's basically offset in just the way that it's hiding between 2 pixels. You can check for this and just eliminate it because it won't actually show up on screen. You can see if it's inside the frustum of the screen. That's fairly easy. Just see if the whole triangle will be clipped. And finally, occlusion, which we will get to in a minute. Their solution depends on multi-draw indirect. I believe it depends on bindless. I'm not entirely sure. And it also has a CPU rasterized artist generated occlusion source, which is a lot of words, but basically it is a very low poly model that the artists have gone and made of the model of the level so that it can render to this 100 polygon thing on the CPU, generate a low resolution depth map, and then use that depth map for the occlusion culling. So more formally, you rasterize the major occluders. So this is walls, buildings, anything big and might occlude a lot of things. That is one way of doing it. You can also do a depth pre-pass, and you can finally do a variety of I don't know if it's temporal, but one of those techniques to basically use time to your advantage so that you can reuse depth in some way, and we'll get to that in a second. So temporal occlusion is not new. We've been doing it for a long time. We've just now gotten pretty intolerant of popping. I have a very vivid memory of playing Wolfenstein, popping around a corner and it taking exactly a frame for the enemy to pop into place. Because they were obviously doing some sort of CPU-driven occlusion culling that needed a frame to get the results of the GPU back on the CPU. It still happens. You can still see like base Unreal games doing this. I don't think it's really tolerated anymore, and we have the technology to not do this, so I'm going to hold myself to a higher standard. So one of the ways we can do this is when we start a frame, the first thing we do is we render last frame's culling results with this frame's transforms. So we've done all the culling for last frame. You take those, you render them to the screen. That gives you a depth map of all of the objects that were visible last frame, all the triangles that were visible last frame, and you can use that as a thing to cull against. And the important property of this is that you will never get a false positive. You will always only get false negatives. The false positive case is when a triangle that would have been visible last frame is no longer visible, and that's already handled by the GPU. The GPU will not participate in the frame because it's hiding behind something, and standard depth checks will cause that to stay hidden behind. So once we have this depth map, we can then do culling against that depth map, and then whatever false negatives you get whatever false negatives you get, you render to brain fart. Yeah, you render the false negatives, which are all the triangles that you culled that you see are visible this frame, but weren't visible last frame. So that way, if you move the camera and then all of a sudden some more triangles are visible, those triangles will get rendered in this last pass to make sure you don't have pop-in. All right, so that's sort of the high-level theory, and hopefully this will clear up as it goes. And if any of this doesn't make sense, please hammer me with questions. I'm sure I missed some part of this. I've been thinking about it for a long time, so actually getting this onto describing it I may have missed some things. So, first is how do we actually execute on this triangle culling shader? So the concept is hierarchical, of course. So objects of a given material are batched into batches of 256 objects. That is the limit of any one batch. So if I have 1,000, I will make 4 batches. If I have, 5, I will still make 1 batch, just with only part of it populated. Before the batching happens, objects are sorted so that all draw call compatible ones are next to each other in that list of objects. So basically, we can just run down the array and figure out, if these objects remain compatible, we can put them all in one draw call, and so each batch contains regions, and this region is the section of objects that can be drawn in one draw call. Importantly, regions never span beyond one batch. So there is one batch for each. There's one region for each batch at least, and regions can't cross batch boundaries. So, for example, say we have 128 objects of one type and 128 objects of a different type, and for some reason either they don't have the same textures, and we're running on a bindful model. Those 128 will be put into different regions, but still in the same batch. I think that makes sense. So, it's too big again. Darn. So how do we actually execute on this compute shader? So we do one dispatch per batch, and then one invocation per triangle. Each invocation finds which object it is by a binary search in the objects list. So as you can see here, the object range, which is the struct per object, has an invocation start and an invocation end. This is the actual invocation index, or the range of invocations that object should occupy, because we need one per triangle. But the amount of triangles in each object can be vastly different. That one could have 45 triangles, and the next could have 45 million. And so we need to be able to deal with the fact that there are different lengths. And because we don't know about that ahead of time, we have to literally binary search our way to find which object any one invocation is supposed to be dealing with. So, invocation 1000 would do a binary search over this list of objects and then find the one that starts at 768 and ends at, 1200 or whatever. And then use that object as the one it should be calculating for. Once we've done this, this triangle is then culled. So there's a lot. This culling shader has a lot of outputs. First, we have these two categories: this primary and the secondary. The primary is basically the proper results of the culling. Every single triangle that passes culling will be in this primary thing. The secondary one is for all of the triangles that passed culling this frame, but failed culling last frame. This is for filling in all of the gaps missed by that first pass. So if a triangle passes culling, it's added to the primary. If a triangle passes culling but didn't pass last frame, it's added to the secondary set. My dog. So, I can't even read that. How fun. So every time a triangle passes, a 3 is atomic added to that vertex count in the struct. So each region has a single draw call allocated to it, and when a triangle passes culling, we atomic add 3 to that vertex count, which gives us two things. One, it makes the indirect call value larger so that it will actually render that triangle. It also gives us a location in the output index buffer to put our data. So this is a fairly standard pattern where you have an atomic and you just add onto it in order to allocate spaces in a buffer in arbitrary order. You don't care about the order of the results, you just need a particular space to put your stuff. The result of the So for transparency is actually fairly well defined in the base API, in that you have to render everything. The GPU has to render everything in basically triangle order. So we too need to preserve the order of triangles when dealing with transparency, because objects may depend on that order. Because of that, we can't do this atomic system, because the atomic system reorders the indices arbitrarily, because the order in which the atomics happen is completely arbitrary. So instead, I'm gonna figure out how to just don't cheat and go ahead. So for transparency, we don't compact them, but we do give any culled vertices, or any culled indices, that should say, a special value. It's 2 to the 24 minus 1. Specifically, so that particular value will represent this index is actually invalid, you shouldn't render it. So meshes are limited to 2 to the 24 minus 2 vertices. This is because every index is... I explained that the wrong way around. Every index is packed. The top 8 bits are for the index within the batch. So a value from 0 to 255, because there's 256 objects in a batch. And then an index value. That index value is what you would expect an index to be. It is an index into the vertex buffer. And because we limit meshes to 2 to the 24 minus 2, that actually gives us one value at the top of every there's 256 possible objects the very top value in the index value, so U24 max, is reserved to basically be invalid. In this case, we always set these top bits to 0, but you potentially could not. And then this is all packed inside of a U32, which is put inside an index buffer in the standard GPU index like pipeline thing. We also need to store our culling results, and because we're doing culling on the, we need to be able to compare our results with our previous results. So the culling shader is provided for every object. You can actually see it in here, the previous global invocation, which tells you where in the previous results buffer to go and look for the results of your triangle last frame. The order may have changed, but the data is still there. So we use bitpack booleans. Basically, this is the process: is that you do an atomic OR into workgroup memory for basically packing 256 bits into 8 U32s, and then once you do all that atomic OR into workgroup memory, for context, atomics into workgroup memory are apparently faster. That at least is the rumor. I haven't verified it, but it hasn't been slow, so I haven't checked. We then do a workgroup barrier to make sure all of the atomics are finished. And then the very lowest in that particular workgroup goes, loads all the values, and writes them to the result buffer. So now we get 1 bit for every single triangle. Gives it nice and dense, prevents all sorts of memory issues, gets that all nice and clean. And we do a similar thing, how you'd imagine. You just load the value, shift, and mask to get the actual particular thing. That, of course, is very quick on GPUs, which have bit field extract. Okay. So, as you may have been able to gather, that all of the vertex data is gotten via vertex pulling. We get this index value, and that index value doesn't actually tell us an index into a buffer. It just tells us this packed piece of data, which object within the batch and the actual index. So we decode that, take that local object ID, look up in the batch data to see what its global object ID is, and then we can use that value to go and pull all the information we have about the object, the transform, the whatever. Inside of that object data, it also includes all of the basic. They're essentially pointers. They're literally U32s, but they're basically pointers into the vertex data mega buffer, saying, "Oh yeah, your position data starts at byte whatever. Your normal data starts at byte whatever." So we have all of that on the object. Once we get those positioned, we pull the vertex data as normal. We explicitly, for any kind of weird formats, like we basically do, the buffer itself is a buffer of U32s in the shader, and then we take that U32, we bit blast it to float if we're reading a FAC3, for example, for position, and then we just do 3 loads in a row, and most shader compilers should be able to combine that when they're actually writing out assembly, so that it will show up as a single load 3. So that I could get into a little more detail, but that's sort of the high level of how that works. It's basically a question of how do you get all the data up to the GPU in a place that you can actually access it. This, for example, has 3 different. Is it 3? I think it's 3 indexes to get from the base index value to all the way to the actual vertex data. But in practice, this doesn't seem to be a problem. There's a lot of hubbub about dependent loads back on older hardware. It doesn't seem to matter anymore. I'm sure someone will correct me that, in some edge case it's actually slower, but, for now, this is what we got. So the vertex shader actually sometimes gets told to render invalid geometry. For example, it gets told to render when an index value is this trap value we've specified. Sometimes an object is deleted, and we need to not render it. Remember, for the majority of the frame is rendered by drawing last frame's culling results. An object could get deleted in the time in that frame. So we need to make sure we're not showing it this frame. So we check on the object, there's a quote unquote Boolean that says whether an object is enabled. If it's not enabled, we just return degenerates. In this case, we actually return vertices. We always return the value 0 for all 0, 0, 0, 0, which is probably undefined behavior because you're dividing by 2, but sorry, dividing by 0. Anyway, we pick a value. We always output that one value. That way the rasterizer can easily see, oh, this is a 0 area triangle. Let's get rid of it. Now, yes, we do 0 area culling in the compute shader, but this is for dealing with particular edge cases that should not show up very often. So we just need this check to make sure the vertex shader doesn't show us something we aren't supposed to see. So that's a lot of words to explain that, and I'm sure there will be tons of questions. But we are moving on to everyone's favorite section, performance. And so I need to caveat this before we do anything, before we go on it. Technically speaking, the branch I have for doing triangle culling has multiple bugs in it. If I were to show it to you, there's many visual artifacts, but I know what all of their problems are, and they should not affect the performance numbers. I was basically in a mad rush to get all the code written for this presentation, so I intentionally ignored some bugs. But all of those bugs should not have a performance, should not influence the performance numbers that I'm pulling here. But they might in a very slim chance, so I'm putting this disclaimer here. Alrighty, let's talk about, this is my favorite model for testing all sorts of basically triangle spam. This is a Unity model exported to GLTF incorrectly, such that all of the LODs are visible at all times, which gives this nice property of just having too many vertices. Makes it a very difficult scene to render, particularly on AMD GPUs. So, and this is one particular look inside this crate thing, where you can see a lot of geometry out through the doors, but the majority of things are actually occluded. This is a very good test of occlusion culling. So let's take a look at the numbers, and they are actually much better than I expected. We have numbers here for both 4K and 1080p. For example, a lot of my information is from AMD, so we'll be doing some deep dives into AMD's performance in a bit. But as you can see, that the relative throughput of everything, even the Mac and the M1 Pro, which is something I was particularly worried about, that's not 308%, that's like 200. I forgot to change that number. Is all positive. And all significantly positive too. We're seeing 1.8 to 3 times performance boost through this process. And that is, I think it's I got very accustomed, especially after my last talk, of seeing performance numbers like 10 times faster, 20 times faster. But on the GPU, getting shrinking the amount of time you're spending by even 1.5x, that is a significant difference in the amount of stuff you can render and on what hardware you can render it. So this is a view of the same map, but with basically everything visible. There's 2.1 million triangles in Frustum. That's 68 million vertices. And for this one, you can very clear. There's also massive benefit. AMD took 30 milliseconds to render this frame on the old version, and the new version takes 7.7. And this is because of both small area culling, occlusion culling, where the majority of the thing is actually still occluded, and all of that. Something to note, the CPU times are significantly worse. This is basically because I've been focusing entirely on the GPU and haven't done a lot of work on optimizing the CPU side. And the old 0.3 was hyper optimized after my first talk. So I'm putting that here for transparency, but at the same time, don't read too much into it. I'll likely fix a lot of those issues before even 0.4 comes out. Now, here's another scene, which is the bistro scene. There's 1.4 million triangles in Frustum here. And we see this is a lot harder. This is for when I say native, I mean the native resolution of the Mac. I'm not sure what the exact resolution. It's a little smaller than 4K. As you can see, the throughput here actually is not great. It's 1.3, 1.05, not significant difference. And this is because there's so many less triangles in this scene. And a lot of the culling is just simple object-based Frustum culling that's happening on the CPU. So there's not both 0.4 and 0.3 have CPU side Frustum culling, just for like, if it's obviously not visible, just don't draw it. So, but these numbers are not great, and they kind of got me discouraged at first when I was first looking at it. But there's a couple things that will show just how much promise this idea has, even if right now we aren't seeing the numbers we hope to have seen at the beginning. So let's analyze the sci-fi, the one in the crate, the one with the red and blue, on the AMD 580 at 1080p, not 4K. I chose 1080p because that card is definitely not made for 4K. It is a 1080p card through and through. So putting it at 4K is basically an unrealistic test because there's just so many pixels. It's having so much trouble shading all those pixels as it is. So as we can see, we get about approximately 3x, a little less than that, performance delta between 0.3 and 0.4. And as you can see, if you look at the difference between the times of opaque, of rendering all the opaque geometry, there is negligible cutout and transparent geometry in this scene. Is that on the old one, it took 5.1 milliseconds. And this is 5.1 milliseconds after doing a depth prepass. So we should have potentially 0 overdraw in the pixel shader. So this is all coming from vertex processing. Because of all of the culling we're doing, in 0.4, we're getting an opaque time of 1.2 milliseconds, which is wild. It is 4 times faster, a little more than 4 times faster. Creating the high Z buffer for culling takes 0.2 milliseconds, and the culling itself takes a whole millisecond. And despite how much the percentage of time that culling takes, it still gets us to a much, much lower number. Now, looking at changing all the parameters, we're now outside and on the NVIDIA card at 4K. As we can see, it's still about a 2x increase, and we have this similar similar ratio of the amount of time opaque is taking, because now we are really getting towards, we are just like running pixel shaders as fast as we can because we have limited overdraw and we're not drawing triangles that don't show up on screen. So the depth prepass takes a long time. We can see the similarities means that like this is just vertex processing time. Unfortunately, because the entire scene is visible within the frustum in terms of objects, the per triangle shader has to cull everything. It has to cull all 21 million polygons, and that takes about 4 seconds at this point. So that if we can get that number down, we could see really incredible deltas on this scene. And this being at 4K also is putting a lot of pressure on the pixel shader as it is, yet the opaque time is still 1.7 milliseconds. And as you can see, there's a lot. The scene doesn't actually cover a large chunk of the screen, so there's not as many pixels to render no matter what. All right, so let's take a look at AMD's trusted Radeon GPU profiler to get some comparison. So this is the view inside the crate at 1080p at 580 on the 580, which is what we talked about 2 frames ago, or 2 slides ago. Thinking about frames too much. So it takes, there is a time here, you just can't see it. And boop. You know what? I'm just do it from here for now. Yeah. So we have. What? Hello. Okay. Sorry. Technical difficulties. So before, you can see that it takes 5.1 milliseconds, and most of the time is just spent with the GPU doing nothing. Whereas now it's 1.2 milliseconds with the majority of the time just pure pixel shading, doing as much as possible. The vertex shader is also taking up more of the space. This is actually our occupancy limit because of how many registers the fragment shader needs. So we can't get this any higher at this current point, but there are potential ways of improving that going forward. But you can just see the difference in the utilization between before and after that shows that this is actually doing what we wanted it to be doing. Then we can talk about High-Z. And High-Z, if you haven't heard of it, is hierarchical Z buffer, which is basically making an airtight bitmap chain of your depth buffer. And because it's a bitmap chain, it requires the sort of naive way is to render from one to the other, to the other, to the other in many passes. And as you can see, despite most of the time is spent, rendering 5 pixels, and because of the need for barriers between each draw, you're just spending a lot of time dead in barriers. That's, I don't know why this is 1.2 milliseconds. This is 0.18. This can be improved by using AMD's single pass downscaler, which can do this all at once and significantly quicker. Just haven't implemented that yet. Finally, let's look at culling. So you can very clearly see each batch in the draw. We do the usage spikes and then it fades out as the batch ends, and this is because the way web GPU works is that each dispatch is its own usage scope. So every single time you go to a different dispatch, if you're using the same resource, you have to insert a barrier there, because potentially you could be reading from an element that you were writing to before. in our case, we know that we're not, but we're still using the same resource, so WGPU doesn't know that. We could implement parallel compute passes. This is something that's been talked about actually both for the upstream spec and for a native extension, which would relieve all of these barriers causing all of these pipeline stalls between every single dispatch. And through my estimates, that would give us, 1.25 to 2x performance just by squishing together and making sure that we're constantly dispatching as quick as we can. There's also some optimizations within that shader that we could do to make the shader more efficient. And of course is the possibility of doing object or meshlet culling, occlusion culling, to relieve pressure on the triangle color. For example, in this scene, a lot of the time is spent dealing with excuse me, one second. A lot of the time is spent dealing with triangles that are components of objects that the entire object is not even visible on screen. So if we could do object level occlusion culling or meshlet level occlusion culling, we could potentially, relieve a lot of the pressure on the triangle color and shrink this time significantly for a much lower cost. Because meshlet culling would do, 1/256th of the work that this is doing, and eliminate maybe half of all of its potential, all of the triangles it has to cull. How we would do meshlet culling despite not having meshlets is that if you run the same kind of algorithm where you have nearby vertices all together, you can then basically attribute that range of indices to a quote-unquote meshlet and treat it as generate like cone. There's a whole thing about cone culling in that presentation that talks about how you would actually go about culling this. So those are all possibilities, things to look into. But potentially, just throwing numbers out there, we're talking 1.5 to 3, 4x what we have now, putting all of these techniques combined. So there are still a couple issues with this thing. Yeah, so your depth data is now not available in the fragment shader. Because we do this thing where we render before we render everything, the majority of the scene, before we generate the high Z buffer, we aren't able to use that high Z buffer for doing things like SSAO or SSR or any kind of screen space, traverse the depth buffer kind of things. However, thankfully, it is fairly tried and true to use reprojection, to use last frames depth buffer for all of these techniques, and a lot of the techniques are not particularly sensitive to frame over frame discrepancies. So this tends to work pretty well. You could also potentially use this technique as a whole to generate a G buffer without a lot of overdraw, and you could use the standard deferred pipeline from there on out. It's not particularly mobile friendly. It forces render passes to store before the culling and then load after the culling to finish rendering all the triangles. This does have an effect on Mac, but we still actually end up ahead on Mac in all situations, which is great. And then the culling results use a non-insignificant amount of memory and does do a lot of memory writes, which mobile chips do not like. Finally, we need a lot more CPU optimization, and we need to fix the bugs. So this is all stuff that will come as part of cleaning all this tech up and moving it to actually be merged into Ren 3 trunk. Yeah. Finally, some acknowledgements. I'm doing nothing that hasn't been done before in some form, so just want to explicitly shout out the various talks that I pulled this from, and I'm standing on the shoulders of giants in terms of that. Then, quick shout out to my employer, actually Modify, who's giving me time to giving me work time to maintain WGPU so that I can use my free time to do this nonsense. Incidentally, we're hiring, so if you want a job, take a look at our listing there. Finally, thank you to all of the GitHub all of the people on GitHub who have sponsored me. That's the words. Throughout the year or so. And there's also something that was cut off that said +4 anonymous sponsors. So thank you to everyone listed here and the 4 anonymous sponsors who also sponsored me. And want to sponsor this nonsense, there's the link to go give me some money if you so choose. The end.
Wow, Connor, thank you for showing this amazing technology to us. I'm going to ask you some questions, and I want to start by saying that your project always pushed the web GPU ecosystem to the max, and you introduced the bindless stuff, and it's very exciting to see how far you're getting, and it's proving that things can be built, and I'm hoping that you can fix the issues that you have currently in the future and like get this to production in some way. This is very nice. My first question is, what is the state of the compute passes without synchronization between dispatches? Is this something that you think is going to be a part of the web GPU upstream, or just WGPU native, or?
I have no idea. I'm still not particularly involved in the standardization process.
Okay.
So definitely on native, like there's no reason we can't implement that. And I would hope to see it on upstream because this does actually have a significant effect, particularly when doing a lot of dispatches on the same buffer. You get a lot of what are essentially write after write hazards on the same buffer, and it is a big problem. So getting that on the web would really help performance there. But if we don't get it, we don't get it, and we'll just have to live with the performance of that. And so be it.
Right. You mentioned 1.5 to 2x improvement potentially getting from this. And I think it's a very good example to show to the group as an argument towards this feature. So I'm looking forward to this. Always found this to be lacking, this particular synchronization bit.
Yeah.
So that's cool.
In particular, I'm still doing fairly large dispatches here. They just happen to be running very quickly. If I were to do smaller dispatches, and I actually had this problem before I came up with the whole region thing, I was actually doing basically one dispatch per draw call, which when I'm running without bindless is actually a significant amount. And the majority of this thing was not occupied at all because it just kept having to flush and flush and flush. So being able to put the compute pass in a parallel mode could mean that even with those tiny dispatches, I could still get decent utilization of the GPU.
Right. The next question is from Discord. How do people use these changes once they are released in 0.4? Is it sort of an option, or is it mandatory, or like how do the user enables it?
So currently it is mandatory in the way that nothing is ever mandatory in Ren 3. So the design is a layered design where you have this core data model within Ren 3 that deals with the render graph. It deals with like vertex data and material data and whatever. And then we have this routine, this reusable render routine built on top of it, which is the one that is actually doing all of this kind of thing. So the core doesn't actually care that much about what I'm doing to draw it. It just provides the data, the vertex data, the object data, the material data, and then I go and render it here. So by default, if you pick up 0.4 and you just use it for rendering, you'll be using this technology. If you want to write your own render routines, you'd have to integrate with how the culling provides you data. But on the other hand, if this is not particularly appealing for you and there's not a reason to use this, you can actually just sidestep that and pull your data directly and, calculate your draw calls yourself and just go forward. This is actually one of those places that Ren 3 story is not nearly as developed, and where I want to focus a lot of my attention going forward is how do we get more graphics tech in terms of like actual, make sure I have IBL, make sure I have all the standard kind of stuff for rendering, but also make it so that you can easily put in your own code without having to rewrite tons of stuff. We are sort of about halfway there on that side. Just needs some more iteration, needs some kind of end-to-end tests, not literal tests, but like trying to do it myself to see what the hurdles are and make those easier.
Right, makes sense. The next question is from me is, are you running this with the full bounce checks of WebGPU? And I'm asking because there's a lot of data operations, there's a lot of indexing I'm seeing, and it's been a concern from the beginning that because WebGPU is safe, it can't allow you to do out of bounds checking, and it's going to be slow. And your numbers are great, so I'm wondering, like, how do you do this?
I haven't turned off anything. Whatever WGPU implements as of like, I don't know, 20 commits ago, is what I'm doing. I actually did intend on doing a comparison with unchecked shader modules to see if that improves or whatever. But it'll be interesting to see that. Because we have that flag so easily available to just be like, hey, make them with no checks. I don't expect there to be that many checks on a lot of the tests I'm doing because I'm running on Vulkan on a RBA2 supported card, so the hardware should be doing all the checks for us. But those MAC numbers do have bound checks like everywhere, so that's very good. It shows positive that this may not actually hurt as much as it seems.
Yeah, that's great to hear. My last question, I guess, is you mentioned there's a few known issues right now because you are in a rush to finish this and they don't affect performance. Can you give a high-level overview of what those issues are?
I can do one better and just show you. Where's all right, let's go into distro full, distro. This is actually a good place to talk about a little bit of the nuance at implementing a couple of these things. So right now there's no shadow maps. This is expected. I just ignored them. As you can see, some of the floor is actually not quite there. It's being occlusion culled even though it is visible. I suspect the issue is that when you're downscaling when you're generating a hierarchical Z buffer for a depth target that isn't a power of 2, you actually sometimes have to sample 3 texels to merge the 3 of them together to find the minimum value. And because I'm not doing that right now, I think I end up missing some values, causing various things to pop out when they shouldn't, particularly ones at steep angles, like the floor here. So once I implement airtight high Z, that issue should go away. There's one. Another one is if I move around, you can see the geometry just like goes cuckoo every little bit, and now I can't get it to do it. What? Yeah, you can sort of see it there. There we go. Going crazy. That is actually is a it's a bug with a very early part of this whole process where I'm just rendering last frame's data. Something goes wrong. I'm not sure if there's some sort of data corruption or like I'm reading the wrong value kind of thing. I haven't quite narrowed it down yet. But the important part is if you stop moving the camera, it completely goes away because all of the values are the same. And all of these tests were done with the camera still. So that was not a particular issue. You can't see it here because I'm running on my NVIDIA card right now, but on the AMD card, non-uniform indexing is broken. WGP does not annotate the texture access as being non-uniform correctly, which means AMD doesn't generate its serialization loop, which means everything is sparkly, and you're basically reading random textures sometimes, which looks very cool, but it's not what I wanted. And then I think there may have been 1 or 2 other small issues, but that is the majority of it. And of course, I have to get shadows working, which is just I haven't implemented that yet. All of these things should not affect performance in a way that skew the numbers.
Very nice, thank you. I'm looking forward for 0.4 release. I think I don't have any other questions, and I'm not seeing anything on YouTube either or Discord, so we can start wrapping this up.
I also need to solve some DX12 issues because I really would like to, when I release, to be able to run on DX12. So there's some knock-up bugs in DX12 generation. Oh, sorry, HLSL generation that need to be solved. So that's about that.
All right, so I will just wrap up the stream here for today. So thank you everybody for coming out. We had 3 great talks today, kind of taking a look at 3 sort of different graphics libraries, engines, and that kind of stuff. And so we'll be posting all these as their own YouTube videos to the Rust Game Dev YouTube channel, so you can go back and take a look at them. I believe the slides for all of them will be available as well, if you want to go take a look. And so thank you very much for coming out, and we will see you next time.